Thanks for being here again. Trying to finish up some of the stuff with light behavior. So we're going to go through refraction math. Encourage you to take notes with this. There's a couple of math examples. You're going to be expected to know how to do these problems. They're pretty simple. They look a little funky because of the formulas that are in them, but with a little practice, it should be very easy. So again, encourage you to jot some things down that you need to. It'll make things a little bit easier. Shouldn't have to answer any questions as we go through this, but a little bit of review and a little bit of new stuff. So we've covered this a little bit before, that refraction is the bending of light as it travels from one medium to another. It occurs because the velocity changes when it goes from one medium to another one. And just notice that my stuff is not quite in the screen there. So the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. If it goes into air, if it goes into water, if it goes into glass, it's going to slow down. When it does that, particularly, well, when it goes in and it slows down, and if it does at an angle, when it goes into it, it's going to bend. All right, so light doesn't need a medium to travel, and if it does go into a medium, then it changes its speed. Right, so a couple key notes about refraction and how they kind of affect sometimes our daily life. Just understanding that light travels from the object to the observer's eye. So when you're looking at something in front of you, no matter where it is, you're seeing it because light is coming from that object to you. And again, it's coming in a straight line. The light travels at different speeds in different mediums. I know I should say not in different, but in different mediums. Just went over that. And our terms to know is when we're trying to analyze where things are going is a normal line. Again, the normal line is going to be drawn perpendicular to the where the surfaces meet. So in this example with the cat and the fish, cat's up here in the air, the fish is down here in the water. So this line across is the barrier between the air and water medium. The normal line is going to be perpendicular, and that's where we're going to use to be able to figure out where is the light going, where is it bending, so forth. So we also label some angles in here. So this theta, in this case, it uses the I because this is incident. So this is usually talking about where is the light coming from. And then we're looking at this other angle. Notice it's between the arrow and the normal line. So when we refer to an angle, anytime, we're referring to an angle, we're measuring it from the normal, from the perpendicular. So we're looking at this angle down here with the fish, and we would be looking at this angle up here with the cat. Okay, so as light goes from one medium to another, part of it ends up being reflected, and part of it ends up being refracted. You saw this in your PhET simulation. So the angle of reflection should be exactly the same. It bounces in and bounces off, but the angle of refraction is going to be a little bit different. All right, so one of our rules here, if you look at from left to right, if we're going from air to glass, we would expect the light to slow down because glass is more dense. And so what you see when it's refracted is the arrow bends towards the normal line here. So that's one of our rules. When light slows down, it bends towards the normal. And the opposite's happening on the right-hand side. If it's going from glass to air, it should be speeding up because it's less dense. And what we see is that the angle increases because it bends away from the normal. Okay, so slows down, goes towards the normal, speeds up, goes away from the normal. So as an observer, oftentimes things don't appear to be where they are. All right, so our brain thinks that light is traveling straight, and but it doesn't take into account refraction. In this picture on the bottom left, if there's a cat standing up here on a pier looking down and seeing a fish, the cat thinks the fish is where it is because if the cat's seeing things in a straight line, and the cat's brain is not taking in the concept of refraction. When in actuality, I don't know where one of them disappeared to. When in actuality, the fish would be down here below. And the reason the cat was seeing the fish where it was because if I extend this line straight that the cat had, the cat thinks that the fish is going to be right here. But again, in actuality, the fish is going to be a little bit low because the light was bending. Same thing with the fish and the cat. To the cat, if the fish could see the cat, it would think it was straight up here, when in actuality, the cat would be a little bit lower. So the bending of light can cause some little changes in our brain. So let's get to the math because all that should have been review up to this point. There's a couple of things on your reference sheet that we need to go over. The things look a little bit weird, but we're going to be looking at these two top formulas we've got here. There's N equals C over V medium. So this has to do with the index of refraction. The index of refraction, I'll go over that in just a second. And then we're going to look at the second formula, which allows us to figure out angles of refraction if we know 3 of those 4 things. So again, this looks hard, but they're really not. It's kind of like formulas we've had before, like V equals D over T, and we've got 2 things equals 2 things. It's just figuring out what all these things are. So N is the index of refraction, V is the speed in the medium, theta again is our angle. And again, N shows up here, so it's just the index of refraction. So all we really have is an index of refraction, the speed of light, velocity, and some angles. That's all that we need. The index of refraction, by definition, that's just the ratio of the speed of light in a vacuum to the speed of light in that substance. So this is our formula. I mean, a ratio is always a fraction. So N is the index of refraction. C is the speed of light in a vacuum. Again, so that's going to be 3.0 times 10 to the 8th, always, always, always. And then this V on the bottom is the speed in the new substance. So if we wanted to say what's the index of refraction of water, we would compare the speed of light in water to the speed of light in a vacuum. That's all. The index of refraction is always going to be greater than 1 because the top number is always going to be bigger than the bottom number unless we're just comparing vacuum to vacuum. There's no units for this, it's just a ratio. So some common things, again, we don't need to memorize this, but just to kind of give you an idea. Again, gases down here in the bottom right have an index of refraction of 1 because that's almost a vacuum. Liquids are going to be a little bit higher because the light's going to slow down in a liquid. And solids are going to be usually a higher index of refraction than that because they slow down even further. So again, the greater the number, the slower the light is in that substance. That's all we're looking at. How fast does the light travel through that substance? And this is a ratio that allows us to compare it to the speed of light in a vacuum, right? So typically what we're looking at, if you had something that had an index of refraction of 2, then it's going to be that's basically going to be half. All right, so the speed of light is going to travel half as fast if it has an index of 2. Let's look at a couple of math examples and how we would go about doing this. I'm a watchmaker is interested in an old timepiece that has been brought in for cleaning. If light travels 1.9 times 10 in the crystal, what's the crystal's index of refraction? So your first thing is understanding this is a question about index of refraction. And let's think about other things that it's given. So we're trying to solve for N. We know the velocity in the object, which is 1.9 times 10 to the 8th. So that's where this number came from. It's in the problem. This is on your reference sheet. So 3 times 10 to the 8th. And again, we just make a ratio out of those two with the speed of light being on top. And again, your answer should always be greater than 1. So again, we just take these numbers, look at our formula, put C on top, put V on bottom, speed of light's on top, the speed of the other one's on the bottom, and we get an index of refraction of 1.579. Right. So if you need to pause the video at this point to write this down, I encourage you to do that. I'm going to continue moving forward. But again, you're going to need to know how to work out these types of problems. So I'd encourage you to give yourself an example so that you know how to do this, but I am going to do one more where we solve for something else. Another example, how fast does light travel in fluorite? Now, in this case, I know the index of refraction for fluorite. Because the formula for the index of refraction is 1 thing equals 2 things, you can make a triangle out of it, right? So we know V, or excuse me, we don't know V in this case. That's what we're trying to find. We know N, which is your index of refraction, 1.434. And again, we know the speed of light. So normally, this is our formula, right? But again, you can turn this into a triangle. Anytime we have 3 variables, we should be able to make a triangle out of them. And the way that you need to arrange your triangle, usually the side that's got 2 items in it tells you how to arrange your triangle. So your triangle needs to have a C over a V in it, which means the C has to be at the top of your triangle. And then the N and the V are going to be down towards the bottom of your triangle. So if we rearrange it, solve for velocity, the T is still going to be on top and the N is going to be on the bottom. So again, in this kind of formula, if C is on top, this fraction, C's got to be on top in this fraction as well. Once we've done that, we just plug things in. Again, C is 3.0 times 10 to the 8th. N is the index of refraction. Put that into your calculator, preferably your Desmos calculator, and we get that answer there. That's it. So again, it's different words than you're used to, but mathematically, you're not doing anything differently than you've done when you've done velocity equals distance divided by time or some other things like that. All right, moving on to the other formula that we have, which is Snell's law. Snell's law just helps us to figure out the angles of light. So back with the cat and fish example, the light comes in from the air at an angle and it goes into the water at an angle. So there's four things that are in play right there. It's the index, how fast the light is traveling in the air, the angle that it's hitting the normal in the air, and then the same thing on the other side. How fast is the light traveling in the water in this case, and what would the angle be? So if we know three of those things, we should be able to figure out the fourth because there's a simple relationship. The index of refraction of the air times the angle that it's going in is going to equal the index of refraction for the water times the angle going into the water. So again, if we know three of these four, we can solve for it. We are always going to need to move one thing to the other side. And also as a reminder, if we're solving for an angle, we also have to move the sign to the other side. If we move sign to the other side, we have to turn that into an inverse sign. So sign with a little -1 on it. This is definitely where you might want to write some things down to make sure that you're getting some practice in. So here's an example. A light ray traveling through air strikes a smooth, flat slab of glass at an angle of 30 degrees. So let's draw a picture and then try to find the angle of refraction. So we've got three numbers up here. We've got an index of refraction, actually two of them, and we've got an angle. So we're trying to find the missing angle. Always helpful to draw a picture to begin with. The picture is a little bit off because it's probably best if your arrow from the air actually kind of hits the normal right here. But again, the idea is we've got a ray coming in from the air and going into water, or in glass in this case. So I've got air up here at the top, and I've got glass at the glass at the bottom. The index of refraction in the air is 1.0, and the index of refraction in the glass is 1.52. We know there's a 30-degree angle. And again, the 30-degree angle would be up top of this if it was labeled right. I think this little arrow got moved over a little bit. So again, the 30-degree angle would be between the normal line and this red arrow that's coming in. Should be over just a little bit. So what we're trying to solve for is what would this angle here be? All right. So let's use our formula. Write out Snell's law. It's in your formula sheet, right? N for the index for the incoming or the incident is 1. That's the number that you got here. The sine of the angle. So this was making a 30-degree angle. So that's why we put 1 times the sine of 30. And that's going to equal the index of refraction of the refracted angle, which is 1.52. And we're trying to find the missing angle that we have here. So this is everything plugged into your formula. And again, at any point, pause, rewind if you're not getting things. And then our next step, a little bit too fast for that, is we got to rearrange the formula a little bit. And this one kind of got flipped over. So 1 times the sine of 30 is just going to be the sine of 30, which is what this is right here. And then because we've got 1.52 times the sine of theta, we need to divide out the 1.52. So if I divide out 1.52 on the right-hand side, it goes away. And I'm going to be left with the sine of theta on the r. But if I divide it out on this side, it has to end up being divided over here as well. So you'll see that the 1.52 moves from being multiplied to being divided. And again, for some reason, the math, it got flipped around on this. So the sine of theta r ends up being this divided by that, right? And then the last thing we have to do is, because we're trying to find the angle, we have to get rid of this sine. So basically, I'm dividing out the sine. And when I divide out the sine, it ends up going to the other side, but it becomes the inverse sine. So from here to here, notice this didn't change. It stays exactly the same. Sine moves from the left, and it moves over to the right. So once you're ready to solve for the angle, this is what it needs to look like. And this is what you would end up putting into your calculator, making it look like this. So the sine of the -1, and we're going to multiply that times the sine of the angle divided by that index of refraction. Just as a reminder on your Desmos calculator, how do you get to all of this? Because if you open it up, this is what it's going to look like, and you need to get to your inverse sine. So a couple of things, you need to click onto the function tab, and that's going to open up these numbers, and that's where you're going to be able to get your inverse sine number. Okay. But anytime you're solving for an angle, this ultimately is what it needs to look like in your calculator. Right? Sine to the -1, and then multiply by this fraction. So again, that's why it's important probably for you to write down and take a couple of examples on here. Again, the answer, kind of get my head out of the way here. This will be our answer up here, 19.2 degrees. Okay, so again, you're looking for an angle. So you should be getting an angle number. Remember, you should make sure that your Desmos calculator is in degrees. If you're getting like 0.1 or 0.2 and you're trying to solve for an angle, you might have done something wrong. So again, think about what your number should be. If the incoming angle is 30, then the other angles should be somewhere close to 30. I mean, it shouldn't be like, 120. That's impossible. It should be between 0 and 90. And preferably it should be within, 10 or 20 degrees of whatever number that you started with. That's kind of how your brain fact check to make sure that you did your math right. All right, one more example, and then you're going to have some opportunities to work on your own. So this one, find the angle of refraction of a ray of light that enters column lake at an angle of 25 to the normal. The index of refraction for air is 1. The index of refraction of water is 1.33. Basically the same kind of problem we just looked at. We're just trying to find an angle. So we're going to go through the exact same steps and have everything look the same. So if we draw it out, this is kind of what it should look like. We've got light coming in from the air, going into the water. The index of refraction of the air is 1. The water is 1.33. I've got an angle of incoming or incident that's 25 degrees, and I'm trying to find the angle that's down here. All right, so again, this is a Snell's law problem. So we look at our reference sheet, we write that out. We plug in everything that we need to. Again, we're just trying to solve for an angle. All right, so we basically know the incoming incidence or index of refraction, this is just 1. We know the angle that it's coming in at, which is 25. And we know the index refraction for the other one, which is 1.33. And remember, the sign is going to end up on the other side. Again, your calculator should end up looking just like it was before. The only thing that changes in this problem are the 2 numbers that we plug in right here. So my angle changes to 25, the index of refraction changes to 1.33, and the answer changes to 18.5. So again, that's the how-to. There's nothing overly complicated about it other than remembering how to use your Desmos calculator. And hopefully you're going to ask for help if you need help in doing that when you get some example problems here shortly. Okay. So I know that's only a couple problems, but we're not going to have anything too much more complicated than that. And if we do, we will cross those bridges when we get to it. You've got a handful of example problems to start working out, make sure that you know how to do them. Your answers and how to do them will be provided to you if you need to check your work. And as always, I'm here to be able to go through that with you. So good luck with that. Let me help you when you need it.